All right, good morning. Welcome to Physics 1520. Welcome back if you were here last semester. A special welcome if you were not here last semester and you're new in the class. If you're new in the class, please come by after class and just introduce yourself. I'm Dr. Chabay. My pronouns are she, her, and hers. And I'm really looking forward to this semester because this is some of my favorite physics that we get to talk about. This year we're going to focus on something that we touched on last semester, which is electric and magnetic interactions. It might seem a little odd to spend most of the semester on that, but in fact this is extremely important. This is what holds the world together. This is what makes your cell phone work and computers work and medical imaging equipment work. So this is sort of key of how the world works and also how much of modern technology works. So this will be interesting, I think. So today we're going to electric interactions. And today, what's happening today? Today is a review. For most of you, we're going to review vectors in 3D, and we're going to review electric forces, because we did a little bit with that last semester, but not a lot. If you weren't in the class last semester, it'll be completely new. But this class kind of has a storyline, and the storyline goes like this. So here is an old style light bulb, an incandescent light bulb, the kind with a filament, the kind that flashlights use, with LED glows. And it's just, so here's a light bulb, and you're going to get really familiar with this equipment because you're going to be using it in lab a lot. This is a socket that just holds it and makes it easy to connect wires to it. And so I screw the light bulb into the socket, I connect wires to the light bulb, and nothing happens. And you're not surprised, right? Because you're thinking, it's not going to work that way, you need a battery or something to make the light bulb light. So, let me actually wonder if there's a way to turn the lights down just in front. Never mind, we'll just turn all the lights down for a minute. Or not. Okay. Yeah, that is going down. Okay. All right, this is not a super bright light bulb, so I'd like you to be able to see it. So let's connect it to a battery and see what happens. Okay, so we're going to... I have two batteries here, but I'm in this battery holder connecting it to one, which is going to work okay. And can you guys in the back see that the light bulb is actually lit? You can. Awesome. Good. So we need a battery, and you may be thinking source of energy input. That's right. Okay, but no battery, no light. So you're not surprised. However, it's not all there is to it. So, let's see if I can connect this correctly. This way. There we go. So this is a thingy, technical term. Okay, so it's not connected to my light bulb, and yet if I hold the light bulb here, you may be able to see that it's actually lighting, even though we're not connecting it to anything. Now there's a sort of a more macho version of the same thing. It's just this is harder to understand. It is a light bulb connected to two metal rods. Okay, so it's not lighting either by itself, but it's just a little brighter. And if we put it here, there we go. If we put it here, we see that it actually does light up, even though it's not connected to anything. And that's not because there's something magic in that box, because that's true of this, there we go, this light bulb also. But if we rotate it 90 degrees, it goes out. So that's more interesting. And the goal of this course is to be able, by the end of the semester, to explain in detail everything that's happening in this light bulb and in the wire to make it light up, even when it's not connected to a battery, but when it's near this mysterious device. So that's our goal. And we're going to take little steps, and we'll bring it back periodically and look at it and see how far we've gotten in being able to explain it. But by the end of the semester, the goal is really to understand this in deep detail. So that's our storyline for the semester. This thing, not that it's helpful, is technically called a decimeter wave transmitter. I'm not sure that tells us anything more than we knew before, but we'll have a chance to explore how it works. Okay. And in the process, we're going to learn about some other things. We'll actually have a chance to go a little more deeply into the nature of light. We will see what Einstein's motivation for inventing the special theory of relativity was, because we'll see where that comes up in the context of these studies. So there'll be some interesting ideas that we'll be able to explore as we talk about electric and magnetic interactions in this course. But first, we'll start at the beginning with a review. So a lot of the quantities we'll be talking about this semester are vector quantities, meaning they have a direction as well as a magnitude. And in fact, they're vector quantities, I forgot yellow chalk, vector quantities that are very 3D. So we're really going to be, all the practice about working in 3D last semester is going to be really necessary this semester. So let's just briefly review vectors in 3 dimensions. This, the reading assigned, and some of you have already seen, is a review of the section on vectors in chapter 1. And there's some sort of review homework on vectors here. So in a Cartesian coordinate system, what's called a right-handed coordinate system, the x, y are all perpendicular to each other, and it's called a right-handed, we always work with a right-handed coordinate system. And that's called right-handed because if you use your right hand and point your thumb along the x-axis and your first finger along the y-axis, then the next finger sticks out the way the z-axis has to go in a right-handed coordinate system. And you could have it in any orientation. You could have x down, or your calculus book might have z up, in which case it kind of looks like this. But we're going to work with it this way because it makes a lot of sense in physics to have y go up and x go to the right, and so z comes out of the board at you. But that's also the way VPython, our computational environment, arranges axes. And it's a pretty standard schema. And so in a Cartesian coordinate system, we need an origin. So let's have an origin. There. That's our origin for our coordinate system here. And so that means that we've got the x-axis plus x is going that way, and plus y is going that way, and plus z is going that way, right? And so a location say here, location A in our coordinate system would be, what do you think that is? So what are these coordinates? So the x-coordinate would be 1 meter, approximately. So this is going to be 1. The y-coordinate, half a meter. And the coordinate would be, okay, so -1, roughly -2 meters. And we're always going to be working with SI units here, so everything's in meters. And if we have a location B, okay, what do you think its coordinates are? Okay, 2, 1, and the z-coordinate is the same, isn't it? So it's -2 meters. And what these coordinates are, they're basically position vectors from the origin. So if we put a vector and draw an arrow with its tail at the origin and its tip here, that is that vector, right? And likewise, there's that vector. Yep. And we're going to write vectors this way because a vector is really one thing. It's not a sum of 3 things. Some of you may have seen vectors written. You might have written it like this: 1i plus 0.5 j plus -2. And that kind of gives the impression that we're adding 3 different things, and it's also very cumbersome, so we're not going to use it, but it is legitimate. And we'll talk about what I, j, and k are in just a minute. So every vector has a direction, and the direction of these position vectors goes from the origin to the location on the board. It also has a magnitude, and the magnitude is basically the length of that vector, if we're talking about distance. And so if we call the vector pointing from the to this location r sub a, and we always write vectors with an arrow over them to show that they're vectors so that we don't get screwed up in our algebra and try to divide by them or something like that, which is not legal. Then r has a magnitude, which we calculate with the Pythagorean theorem. So it's just 1 squared plus 0.5 squared plus -2 squared. Take the square root of that whole thing. And that comes out to, I don't know, so has anyone calculated it, or should we just calculate it here? So, So RA is vector 1, 0.5 minus 2. Magnitude R of RA is square root of 1 squared plus 0.5 squared plus minus 2 squared. Oops. Wait. Okay, so my program, so what did I do?
You have to put the to the power of 2.
No, you have to put quotation marks.
There's a double asterisk waiting for it too.
That's probably better, huh? Not a number, okay.
You can just use the mag function.
Yes, I know I could do that, but I was actually trying to do it this way.
Yeah, just take the.
That doesn't look like it likes
Parentheses around the negative.
Well, how about that? There we go, yes. So this is equal to 2.29, and as you so cogently point out, this is a lot more work than we have to do because since we are doing this all the time, we can just, instead of doing this, we can just use the function makeup of name is mag of RA, and we didn't have to do all that work because VPython knows how. You will be able to use computers on tests. All the tests are in Sage 330 again. So it is, and I certainly recommend using this for homework where it saves a lot of effort in these calculations. So getting used to this is good. Now, every vector can be expressed. So a vector is something that has two things. It's got a magnitude and a direction. So the magnitude is a scalar. It's not a vector. It's just one number, right? And any vector can be written as a product of its magnitude, which is a scalar, times a vector of magnitude 1 that's pointing in the same direction, and that thing is called a unit vector. When you multiply a vector by a scalar, all you do is multiply every component of the vector by that scalar, so it would be 3 times 1, 3 times 0.5, 3 times minus 2 meters. Multiplication, you can also multiply by 1 over 3, which is equivalent to dividing by a scalar, the same thing. So we want to write RA as the product of two things. Its magnitude times some vector that but has magnitude 1, and that's a unit vector. And so unit vectors have a little hat over them. And to calculate a unit vector, what we do is we just calculate the magnitude of the vector. We calculate the magnitude of the vector and then divide the vector by its own magnitude so that we can, so basically, so let's calculate the unit vector R hat, RA hat in the direction of RA. So what we're going to do is going to divide 1, 0.5, negative 2 meters by 9 meters. And that means we're dividing everything, so we could do this. Well, VPython makes your life simple, okay? So we can say RA hat is RA divided by the magnitude of RA, and print that. So does that seem about right? So 1 divided by 2.29.4 seems roughly correct, right? So so we get 0.44, 0.22, and negative 0.87. And notice that a unit vector has no units because we divided meters by meters and they cancel. So the units in the vector go with the magnitude here. And this is going to be useful because often there are quantities where we can calculate a scalar piece and then we just want to add a direction, and that's what the unit vector is good for. It gives us a direction without changing the magnitude of something. So, questions so far? Okay. All right. So just to be clear, we got that result by dividing 1 by that, dividing 0.5 by that, and dividing -2 by that. Yes?
And you can check by taking the magnitude of the unit vector. It should be 1.
And that's absolutely right. So Flavia says you can check by taking the magnitude of the unit vector, it should be 1. So if you want to make sure you've actually gotten it right, let's calculate, we'll call it check, is magnitude of RA hat. And now you think this is going to come out to exactly 1? Probably not quite, huh? Because there's some rounding error going on in our floating point representation. Well, that's pretty close. Okay, we got exactly 1, or at least close enough to 10 to the minus 18th or something. But that's because we kept all of the significant figures that were actually in the computer's memory instead of truncating even to that many. Yeah, Charles?
We can use the hat function as well, right?
That's right. So in VPython, there's actually an easy way to do this. So instead of having to do that, we can go so there's a handy-dandy function built into VPython, the hat function that generates a unit vector. And I know I've used this variable name before, but I've reusing it here. And just to make it clear, we're calculating a different calculation. Yeah. So that gives you. So again, VPython is your friend when you're doing vector calculations. So what else can we do with vectors? We can get a magnitude. We can get let's see. Magnitude. We can get a unit vector which gives direction. So for our so we calculated this vector r sub a hat. What is the direction of that unit vector that we just calculated? It's in the same direction as r sub a, isn't it? So r sub a is in that direction. So r hat, r sub a hat, is also in that direction. So we preserve the direction, but it has a magnitude of 1. We can multiply by a scalar. And in fact, this basically is a form of scalar multiplication because we took the vector RA and we multiplied by 1 over its magnitude. So we're multiplying by a scalar to get this unit vector. We're scaling it down to... What else can we do with vectors? Well, we can add and subtract them. And that's going to be important in this course. So, to add vectors, suppose it's something we did last semester is we added forces to get a net force, right? So if we have an object that's got a force F1 acting on it, but it also has a force F2 acting on it, the net force is going to be the sum of F1 plus F2. And we can add vectors both algebraically and graphically. So to add them graphically, we put the tail of the second vector at the tip of the first vector. So basically, we want to move F2, redraw it here. And then the sum is the vector, first vector to the tip of the second vector. And if we had 3 forces, we'd just add the third in. So vector addition, how do we add vectors algebraically? Well, if F1 is 7, 10, minus 3 newtons, actually, and F2, which obviously has the same z component, so that would be, it's got, I don't know, 5, negative 7, minus 3 newtons. So F net is going to be 7 plus 5, 10 plus negative 7, negative 3 plus negative 3 newtons, or 12 3 plus 3. Negative 6 newtons. And you need to be able to do it both ways. Being able to add vectors graphically is actually extremely useful. So we can add vectors. And that's going to be extremely useful in getting not only net forces, but in calculating the net electric or magnetic field at a location in space. We can also subtract vectors. And one important use for vector subtraction is to find a relative position. So So in our example here, we know the position relative to the origin of location A, and we know the position relative to the origin of location B. But the question is, if the question was, what's the position of location B relative to location A? How would we have to travel to get from A to B? What we want is, we want to know what that vector is. And for that, we're going to use vector subtraction. This vector is R sub B minus R sub A. So it's always final location minus initial location, final minus initial. We've in the past called vectors like this delta R, but we're going to end up calling this typically R is going to be our symbol for a relative position vector this semester. And how would we, so we can subtract vectors. And what do we do to subtract them graphically? Well, what we actually did here was, let's draw this in, let's do a 2D example for a minute just because it's easier to draw. So if here's some location, here's some other location, and here's our origin. So if this is R sub 1, and, oops, that's R sub 2, we want the position of 2 relative to 1. Apparently what we do is we put these two vectors tail to tail. So even if they're not coming from the same location in the problem you're doing, because they might not be a position vector, to do it graphically, we want to put the vectors tail to tail and then draw an arrow from the initial location to the final location, and we get the result. We're going to do a lot of that this semester. Now this is what you did when calculating gravitational and electric forces last semester, so it should be fairly familiar. So that's a pretty quick overview. If this is unfamiliar, you definitely need to study section 1.4 and chapter 1. There's some assigned homework and recitation a little bit. There's some assigned homework on vectors. It's also the case that all odd-numbered problems have answers at the end of the textbook, at the end of the chapter. And so you can find the answers by looking at the whole textbook. If you go to the Read, Study, Practice section of Wiley Plus, then instead of in your reading assignments, just the sections that are assigned are there. But if you want to read the whole thing, then if you go to Read, Study, Practice, you can actually access chapter by chapter and get the whole chapter. So, comments or questions? And VPython, of course, does this for us. It knows about vector subtraction, so we can print, we say R equals RA minus vector 3, 2, 1. We print R. It does vector subtraction and vector addition for us, so we're happy. Okay. So once over lightly, mostly this should be familiar. Questions? Comments? Okay. So let's make some use of this by talking about electric forces. and actually calculating an electric force. So why are electric forces important? Electric forces are important because matter, all the ordinary matter that we deal with, a bunch of other kinds of matter that we don't see very often are actually also charged particles. So they have electric charges. And experimentally, we've found over many centuries that there seem to be two kinds of charged particles. And we could have called them A and B, but somewhat arbitrarily they were called positive and negative. But the basic idea is that particles that are charged positive, or macroscopic objects that have more positively charged particles than negatively charged particles in or on them, actually repel each other. So now this is actually really different from gravitational forces because we only know of one kind of gravitational force. Anything with mass attracts anything else with mass. So repulsion is really a thing particular to electric forces. And negative objects also repel each other. But objects, so objects with like charges, two positive charges, two negative charges, they repel. Objects that have opposite charges, so positive and a negative, actually attract each other. So that's the fundamental experimental basis on which we start. Now we observe experimentally some other things about this force. One is that as you get the objects farther from each other, the force decreases. And in fact, it goes down pretty rapidly. So at some distance d, the magnitude of the force is, well, let's just say distance and the force. So at some distance d, the force between these two particles is, we'll call it F1. At a distance 2d, this force is actually F1 over 4. And at a 3d, it's going to be F1 over 9. So the magnitude of the force seems to decrease. The direction stays the same. The direction is always along a line connecting the two particles. But as the distance increases, the magnitude of the force decreases like 1 over the separation squared. Okay? We also observe that this force depends on amount of charge. So that if we have two positive objects with the same charge, they repel each other. They exert equal and opposite forces on each other, and those forces have, we'll call it F1. If we double the amount of charge here, then we actually end up doubling the forces they exert on each other. So the magnitude of the force is directly proportional to the Now this force also is reciprocal. Reciprocity applies. You saw reciprocity in contact forces last semester when you did collisions between carts. You looked at the force probe. And so we should be able to, and we'll talk about how that works in a minute, but we should be able to put this together into a mathematical description of the electric force between two charged objects, two charged particles. So, in general, we have an object with some charge. For some reason, we always use the symbol Q to refer to the amount of charge on an object. In SI units, Q is in coulombs. The abbreviation for coulombs is a capital C. It turns out that 1 coulomb is a huge amount of charge, so it's kind of an odd unit. But and here's another object with charge Q2. So we're going to write, we want to write an expression for the force on object 2 due to the charge on object 1. So we know that the more charge, the bigger the force gets. So should charge be in the numerator or the denominator of our expression? More is more in the numerator, right? So so we definitely want Q1, and we also want Q2, because if we double either of these charges, then the force doubles. So it's just a direct proportionality. Now this is, we want the distance dependence. It's 1 over distance squared. And the way we're going to talk about distance here is we're going to do everything in terms of the relative position vector, R, which goes from the object that's responsible for creating the force to the object that's experiencing the force. So that's our relative position vector R. So how are we going to use this to express the distance dependence in this force? We know it's 1 over distance squared. So what goes here? Magnitude of R squared. And presumably there's some constant, some proportionality constant. And there is a proportionality constant. And we write it as 1 over 4 pi epsilon 0. So this is a Greek lowercase epsilon with a subscript 0. And the reason we write it this way is that epsilon 0 is the important constant, actually. And the 1 over 4 pi is to get everything to work in SI units. So we're actually going to write this, we're going to use this constant as, keep writing it as 1 over 4 pi epsilon 0, because epsilon 0 has a life of its own. So are we done? No, we're not done, because we now have an equation that's not mathematically correct, because we have a vector equal to a scalar, and that's not cool. So what do we need to capture the direction? Yes, exactly. We need R hat. And we'll find that 1 over 4 pi epsilon 0 has the value 1.6 times, it has the value 9 times 10 to the 9th Newton meters squared per Coulomb squared. And let's see if the units come out right. This is going to be coulombs times coulombs, so we have coulombs squared in the numerator. We have meters squared in the denominator. So we have Newton meters Coulomb squared times Coulomb squared over meters squared, and that should give us newtons, and it does, so we're cool. But let's be sure that this equation really captures the direction correctly. Because these Q's could be positive or negative. And so our hat's always pointing this way. But depending on whether these two things have the same charge or opposite charges, the force could be that way or that way. So we need to make sure that this expression actually gives us the correct direction. So let's consider a couple of cases. Suppose we have an object whose charge is plus 3 nanocoulombs. Nano is 10 to the minus 9th. And another object whose charge is plus 3 nanocoulombs, another 10 to the minus 9th. So this is object 1, this is object 2. We want the force on object 2. The force on object 2 better be that way, right? It's got to come out that way. And here's our R vector. In this equation, we're going to have 1 over 4 pi epsilon 0. We're going to have a plus 3 times 10 to the minus 9, plus 3 times 10 to the minus 9, whatever the magnitude of R squared is, R hat. Okay, what is the value of R hat by inspection? 100. So R hat is okay, so we've got a positive number here. We're multiplying two positive numbers by R hat. And so we a force that in the appropriate direction. What happens if they're both negative? Same thing, right? Because if we had a minus 3 nanocoulombs here and a minus 3 nanocoulombs here, we'd have a minus times a minus times R hat, and we'd still get a force in the direction of R hat, so that works out okay. And just to check, if this is positive and that's negative, what we're going to end up with is a plus times a minus. And now we're multiplying R hat by a negative number. And multiplying a vector by a negative scalar changes the sign of every single component in the vector. So the vector ends up going the other direction. And so we do, in fact, end up with the force going in the right direction. So it looks like this equation captures the electric force correctly. So what are some of the particles that have electric charges? So what's one charged particle that you all know about from chemistry? Electrons. So electrons An electron, it turns out charge is quantized, meaning it occurs in increments of a particular number, which is called, just to add confusion here, E, a little lowercase e. This is not charge on a proton, and it's equal to 1.6 times 10 to the negative 19 coulombs. So the charge on an electron is in fact a minus E, or a minus 1.6 times 10 to the minus 19 coulombs. Its radius is really small. In fact, it's too small to measure. We haven't got a measurement of the radius of an electron, really. We keep getting more lower bounds. There's actually one theory which suggests that the electron is truly a mathematical point, in which case we're never going to be able to measure its radius. But in any case, it's really small. So what's another charged particle you know about from chemistry? Protons. The mass of an electron is about 9 times 10 to the minus 31 kilograms. Protons. Its charge is plus E. So again, we see charge occurring in multiples of 1.6 times 10 to the minus 19 coulombs. Radius of a proton is about 1 times 10 to the minus 15 meters. And its mass is about 1.7 times 10 to the minus 28 kilograms. So more mass.
27.
Probably 27. 27. Let's look it up. Yep. 27 kilograms. Thank you. Now, you've probably heard of antimatter, and there's a little bit of it floating around, not a lot, because every time it gets near ordinary matter it reacts and they annihilate each other. But we can make anti-electrons in accelerators. They also are called positrons. And there's a medical diagnostic technique. They're also one of the things that can be emitted in radioactive decay of some elements, and there's a medical diagnostic technique called positron emission tomography, in which a substance is labeled with a radioactive element that'll emit positrons. Somebody ingests it, it goes to places like the brain, and then you detect positrons coming out, and you can tell where that radioactive tag is gone.
You know, you get the photons from the annihilation of what you get.
Yeah. So the charge of an anti-electron, a positron, is actually plus E. Radius is the same as the radius of an electron. And there's also antiprotons, which has a charge minus E. This is same as a proton. And there's a bunch of other stuff that we see sometimes: muons, pions, lots and lots of charged particles, some of which are created by energetic particles hitting the top of our atmosphere. So we'll run into a bunch of charged particles in this course. And now we can, of course, combine these things to make other objects. And how we combine them determines the net charge of an object. So the simplest thing, combination might be a hydrogen atom, which is one proton and one electron. So the proton sits at the nucleus, sits at the center, and the electron spends its time kind of wandering around in a spherically symmetric cloud. So we have one proton, one electron. We say its net charge is E plus minus E 0. So that's a neutral object if the net charge is 0. If an object has more protons than electrons, it has a net positive charge. So an alpha particle, for example, consists of 2 protons and 2 neutrons. What's the charge of a neutron? 0, right? No charge. And so its net charge is plus 2e, just the charge of the protons. Alpha particles are another thing that's emitted by various kinds of radioactive decay. So there are lots of things that have non-zero. Most of the objects in this room right now have a net charge of 0 because electric forces are pretty strong. And we would notice if we were repelled by the chairs or attracted strongly we couldn't get up. So in general, most ordinary everyday objects are neutral, but we can charge them, and we'll work on that in chapter 14. Okay. Let's calculate an electric force. Okay, so let's actually use our equation here to calculate an electric force between 2 charged objects. So here we'll put an alpha particle plus 2e, and its location is 6 times 10 to the minus 9, 5 times 10 to the minus 9, 0 meters. And down here, we'll put an electron whose location is 9 times 10 to the minus 9, 2 times 10 to the minus, okay. 6 times 10 to the minus 9, 2 times 10 to the minus 9, 0 meters. And we want to calculate the force on the electron due to the alpha particle. So let's actually record our equation up here so that we can so force 1, 2, Q2 to 1 over 4 pi epsilon 0 Q1, Q2, magnitude of R squared R hat, where R goes from 1 to 2. So what's the first thing we need to do?
Figure out R hat.
Yeah, we need R hat. We need R. Need both of these things. So we need to. So what direction does R go? We want the force on the electron due to the alpha particle. So which way does R go? Where does it start? Starts at the alpha particle, goes to the electron. So this is R. Okay. So R is going to be equal to 6 times 10 to the minus 9, 2 times 10 to the minus 9, 0 minus. They can't both be 6 in the x, can they? That's just wrong. That's a 9. Nine times 10 to the minus 9. Oh, this was a 5. No, that was a 2. That's a 9. Okay, we'll get this right. 6. 5 times 10 to the minus 9, 0 meters. Is that right? Yeah. Okay. So we have 3 times 10 to the minus 9, negative 3 times 10 to the minus 9, 0 meters. And that makes sense because the x component is positive and the y component is negative, and so that looks like the arrow we drew. The magnitude of R is going to be the square root of 3 times 10 to the minus 9 squared plus a minus 3 times 10 to the minus 9 squared plus 0 meters. Square root of 18, I don't know, let's ask Python. So R is a vector. 3 minus 9 minus 3 minus 9, 0. If we print the magnitude of R, we can print okay, so the magnitude of R is 4.243 times 10 to the minus 9 meters, and R hat, which is R over the magnitude of R, is that's negative. Okay? So now we've got R, magnitude, we have the magnitude of R, we have R hat. Question? Really, it's fine to have questions. What are we going to do with these values? Plug them into the equation, right? So we've got on the electron is 1 over 4 pi epsilon 0. So let's write that out as 9 times 10 to the 9 Newton meters squared per Coulomb squared. We want the charge on the alpha particle 2 times 1.6 times 10 to the minus 19 coulombs. The charge on the electron, which is minus 1.6 times 10 to the minus 19 coulombs. We want it to be r squared, 4.243 times 10 to the minus 9 squared times 0.7070 meters. And let's define some. QE is 1.6 times 10 to the minus 19 coulombs. 1 over 4 pi epsilon 0 is 9 times 10 to the 9th. And so the force is 1 over 4 pi epsilon 0 times 2 times QE times minus QE. Divided by the magnitude of r squared, the whole thing in parentheses, multiply by r hat. Does that look right? Parentheses matched. We'll see. Yeah. And so we get a force that is minus 1.8 times 10 to the minus 11, 1.8 times 10 to the minus 11, 0 newtons. So does that make sense in terms of direction? It's in the minus x direction and the plus y direction. And so that looks right. What would happen to this force if we move the alpha particle half? How much bigger? 4 times bigger. What would happen if we moved it twice as far away? 4 times smaller. Okay? Good? What would happen if we put another alpha particle right there? What would the net force be? There are 2 forces. So we have to add them. So it would be this force plus a force you just told me was 4 times bigger. So that would be 1, 2, 3, 4. That's alpha 2. And we'd have to add these to get the net force. So it would be 5 times as big, wouldn't it? Yep. Now notice that having another particle in the way doesn't make the force go away. These forces go right through matter. So So nothing happens. It's not diminished. So superposition means we add the forces and the forces don't change even if other particles show up, other charged things show up. Okay. We'll practice this afternoon in recitation. If you have questions, please come up.